going to find the logarithm to be y is equal to log base a of x if and only if x is equal to a to the y. Logs and exponents are inverses of each other. So let's complete the table here. If one column is a logarithmic form and one column is the exponential form. All right, so 3 to the 4 equals 81. To put that in logarithmic form, that's log base 3 of 81 is equal to 4. Now, log base 1/2 of 8 equals -3 means 1/2 to the -3 is equal to 8. 10 cubed equals 100 means log base 10 of 1,000 equals 3. Log base 5 of 1 over 125 equals -3 means 5 to the -3 is equal to 1 over 125. Log base 12 of 12 is 1. And to rewrite log base 6 of 1 is 0 means 6 to the 0 is equal to 1. So to solve log equations, you need to isolate the logarithms, combine your logs, write it in exponential form, solve for x, and then check because you get a lot of extraneous solutions on these. So let's solve these. A is log base x of 16 divided by 9 is equal to -2. So you put it in exponential form. X to the -2 is equal to 16 over 9. So x squared is 9 over 16. So we're going to take the positive square root because remember the bases have to be positive. So x is 3/4. For part B, log base 16 of x is 3/4. We're going to put it in exponential form. 16 to the 3/4 is equal to x. So 16 to the 1/4 is 2. So 2 cubed is 8. Log base 36 of the square root of 6 is equal to x. Means 36 to the x is equal to the square root of 6. Let's get a common base. The common base is 6. So 36 is 6 squared. So 6 to the 2x is 6 to the 1/2. Set the exponents equal. 2x is equal to 1/2. So x is equal to 1/4. Remember, the log function is the inverse of the exponential function. So what that means is if you can graph the exponential, you can just switch the x and y values to find your log functions. Graphically, it's going to reflect across the line y equals x. When you're graphing the log function, the domain is from 0 to positive infinity, and the range is from -infinity to positive infinity. It is always increasing and continuous on its entire domain. It has the y-axis as a vertical asymptote, and the graph passes through 1 over a, -1, 0, 1, and a1. So those are 3 points you can always graph. When a is less than 1, but again, it's still going to be positive, then the function is decreasing and continuous on its entire domain. It has a vertical asymptote of the y-axis, and it passes through the points 1 over a, -1, 0, 1, and a1. Characteristics. Well, as we have just covered, the points 1 over a, -1, 1, 0, and a1 are always going to be on your curve. If a is greater than 1, it's going to be increasing. If a is less than 1, it's going to be decreasing. The y-axis is always going to be a vertical asymptote. And the domain is always the same. It's from 0 to infinity, and the range is all real numbers. So what if we want to graph y is log base 1/3 of x? Well, what you can do is you can graph x is 1/3 to the y, and find the ordered pairs. The ordered pairs for x is log 1/3 of, or y is 1/3 of log of x, are going to be found by switching the x and y values. So suppose we just make a table of values for x and y is equal to 1/3 to the x. When x is -2, y is 9. When x is 0, it's 1, etc. Now, when we want to look at y is equal to log base 1/3 of x, okay, these first three are going to be undefined because, of course, we can't take the log of a negative number. We can't take the log of 0. But when we come to x is 1, well, where is y equal to 1? Y is equal to 1 when x is 0. So when x is 1, log base 1/3 of x is 0. All right. When x is 3, y is 3 when x is -1/2. So the log is 1/2, etc. You can graph these points and you see it follows the pattern with the vertical asymptote of x equal to 0, and it's decreasing. So the graph of this function is a reflection of y equals 1/3 to the x across the line y is equal to x. Graph log base 5 of x. Now this is going to be the inverse of x equals y to the 5th. Doing the same process when we can find the points y for y equals x to the 5th, and then swap them. So for when x is 1, all right, that x value is 0. When x is 2, we don't actually have this one on the graph. For these, you would need a calculator. You'd get 0.43 and 0.68. It's perfectly okay to graph a bunch of these and then swap the x's and y's. Now we see we have a vertical asymptote of x equals 0 and increasing function. Again, this is a reflection across the line y equals x. And how would you graph log base 3 of x plus 2? Well, this is a translation to the left of 2 of the graph of log base 3 of x. It has a vertical asymptote where x plus 2 is 0, so where x is -2, that's where your vertical asymptote is. The domain is from -2 to infinity, and the range is all reals. Now, how would we graph log base 4 of x plus 2? Well, this is going to be a vertical translation up of 2 units. So we still have the same vertical asymptote. The values are simply shifted up 2. The domain is 0 to infinity, and the range is all reals. Now, suppose I want to graph f of x is log base 2 of x minus 3. This is going to be a horizontal shift to the right 3 and a vertical shift up of 2. The vertical asymptote is going to be when x plus 3 is 0 or when x is equal to 3. So put in your vertical asymptote. The domain is from 3 to infinity, and the range is all real numbers. Now let's talk about the properties of logs. The product property says that the log base a of x times y is equal to log base a of x plus the log base a of y. The quotient property says that log base a of x divided by y is log base a of x minus log base a of y. The power property says log base a of x to the r is r times log base a of x. And the log base a of 1 is 0 always. And the log base a of a is always 1. for a, when a is positive and not equal to 1, then a to the log base a of x is x. These two are inverses and kind of undo each other. And similarly, log base a of a to the x is equal to x. Now be very careful when you're writing logs because you're going to be tempted to separate them. Log base 3 of x plus 2 is not log base 3 of x plus log base 3 of 2. This is a function. These two have to stay together. So let's rewrite these using our properties of logs. Log base 7 of 8 times 6 is log base 7 of 8 plus log base 7 of 6. Log base 6 of 12 divided by 5 is log base 6 of 12 minus log base 6 of 5. Log base 2 of the cubed root of 9 is log base 2 of 9 to the 1/3, which is 1/3 log base 2 of 9. Now log base b of rs squared t divided by u cubed v to the 5th, we're going to use the division rule first, and then we're going to use the product rule, distribute our negative. Now, when I do this one, log base a of the 5th root of r cubed, we're going to want to write that as a rational exponent, and then bring that rational exponent out to the front. Now, log base a of the mth root of r cubed s squared divided by t to the 4th, you want to go on and make that exponent first, and then go on and bring it out front. So it'll be 1 over m log base a of r cubed s squared divided by t to the 4th. Use the product rule, and then distribute. Now, here we're going to want to combine them into a single log with coefficient 1. So this one's going to be log base 4 of x divided by y. Then the plus z, the z is going to go in the numerator. So here's the hint. If it's got a plus sign, it's going to go in the numerator. If it's got a negative sign, it's going to go in the denominator. There's a hidden plus sign right here. So log base 4 times log base b of r minus 5 log base b of s. You need to make these exponents first and then combine them. And the same thing with number C. The first thing you need to do is move those radicals, make some exponents, and then you can combine. So assume that log base 10 of 7 is 0.8451. Find each log. So log base 10 of 49, I know log base 10 of 7, so I'm going to rewrite 49 as 7 squared. So this is 2 times log base 10 of 7. So it's 2 times 0.8451, or 1.6902. So what about log base 10 of 70? Well, that's log base 10 of 7 times 10, which is log base 10 of 7 plus log base 10 of 10. Log base 10 of 7 is 0.8451, but you remember log base 10 of 10 is 1. So it's 1.8451.